Can stop this and then view. All right, so 17 minus 2, 15 people online. Okay. We will continue our discussion on Fourier series coefficients. We were talking about the properties. The first property that we looked at was linearity. Linearity includes additivity and homogeneity. So we talked about the property first, and then we used it to find the Fourier series coefficients of this particular periodic signal. So we literally broke it up into two pulse trains. We know the standard result for one pulse train, the Fourier series coefficient, and then we use that twice to, and the linearity property to find the Fourier series coefficients of this sort of a one pulse over the other periodic waveform. Right? That's where we stopped, finding AK using linearity property. Now, the next property that we are going to look at is vertical shift. And we sort of talked about it informally a few times. If you move the signal up and down, and if it is the same signal that you're moving up and down, the only Fourier series coefficient that gets affected is the DC term, A sub 0, the zeroth Fourier series coefficient. Now, how do you prove that? Let's go through the proof quickly. We are assuming that x of t is our periodic signal whose Fourier series coefficients are A sub k. And we are going to add some DC value to the signal, offset it by some constant C. C could be positive or C could be negative. And the coefficients for this vertically shifted periodic signal is BK, right? So what would be BK? The property says that BK is going to equal AK when K doesn't equal 0, which means that all the Fourier series coefficients, except for when K is 0, they are going to exactly be the same. However, when K is 0, BK equals AK plus C, which essentially means B sub 0 equals A sub 0 plus C. So the only the DC term gets modified by the same DC constant C. How do you prove it? Let's start with the formula for A sub k. This is exponential Fourier series coefficient. Integration over one time period, 1 over t, integration over one time period, x of t e to the minus j k omega naught t dt. Do I need to remember this? Do I need to remember this during the exam? Do I? Am I going to give it to you? All right. So the question was asked for a purpose. The purpose was, did you guys see this? The resources page, the last section is general resources, and this is the table of Fourier series properties, Fourier transform pairs, Fourier transform properties. So when I pull up that page, the second equation that I have is the same one that I was referring to, right? So I'm trying to say that you don't need to remember these things, but you do need to know where they are and how to apply them. Let me go back. So linearity property is what we proved, right? So the first one, we are looking at time shift, frequency scaling, and all that as we go on. Coming back to this. So I have the AK here. I wanted to find BK, the Fourier series coefficient of that vertically shifted signal. For this, the only thing that I'm going to change is, instead of having x of t, I'm now going to have x of t plus c. C is a constant. Now I can break this up into two integrals. One is with x of t and the other is with the constant c. But because that is not a time-dependent variable, I can pull it out of the integration. So in the first piece, I've got what? 1 over t integration over one time period x of t e to the minus jk omega naught t dt, which is simply ak. Or in this, and then the second piece of this integration is, because of this C term, I've got C over T, integration over one time period, e to the minus jk omega naught t dt. We have learned that if you are integrating over a complex exponential for one time period, the result is going to be a 0. Didn't we do that? Because e to the minus jx or e to the plus jx even is cosine x plus j sine x. Cosine over one time period, area equals 0. Sine over one time period, area equals 0. Positive cancels out with the negative, which also means that this integration is going to go to a 0 unless k is 0. If k is 0, this guy goes to a 1, this guy goes to a t, that cancels out with this t, and you will be left with just c. That happens only when k is 0. Right? So that condition is written out over here. So combining these two things, we can say bk, the exponential Fourier series coefficients of the signal that has been vertically shifted up or down, doesn't matter, is going to equal ak plus c when k is equal to 0, and it is going to equal ak when k is not equal to 0. Questions about this? How do you prove it? What is the property? Does it make sense or not? Right? I think does it make sense or not is the most important question, right? Taking the signal, moving it up and down, right? So the only thing that I'm changing is not the frequencies that make it up, but just the DC offset. Next, let's apply it. Let us apply it to this particular problem. So what we have here is a pulse train. So what is the pulse train over here? Let me write x of t in my pulse train, the standard form. What would that be? I will say pulse train. And in parentheses, I need to give what? T1 comma t, right? T1 would be 1. And it has a time period of 4. Right? So 0 here, 4 here. So time period is 4. T1 is 1 there. So it's a pulse train with T1 in our standard form. T1 is this guy right here, right? So our standard form is defined as 1 between negative T1 and T1. So it's negative 1 and 1. T1 is 1. I also need to scale the amplitude, don't I? I think I need to add a 1/4 here, right? Because of this guy. Yeah. So I've got 1/4 pulse train 1 comma 4. What would be the Fourier series coefficients of that? Well, I want you guys to sort of help me along here. But I think it is going to be 1/4 is going to remain as is because I've got the scaling. And then I've got half sinc k pi over 2 for all k. As a reference, I'm going to write what I used. I used pulse train T1 comma T equals, not equals, the Fourier transform, Fourier series coefficients of that are 2T1 divided by T sinc k omega naught T1 for all k. Now, what we had in our problem is this. We had time period equals 4. So omega naught became 2 pi divided by 4 half, not half, pi over 2. Right? So that went over here. So we got k pi divided by 2. 1/4 came in from here. 2T1 divided by T became what? 2 times 1 divided by 4, right? 2 times 1 divided by 4. So that became half. Then sinc k pi over 2. Sinc k omega naught T1. Sinc k times pi over 2 times 1. Questions here? AK is, I can simply write this as what? 1/8. So I've used that standard result to help me with that. Questions about how I wrote the Fourier series coefficients of x of t? Okay. Now, this is fill in the blanks that we have already filled. So what was T1? 1. T4, T is 4. And then area was what? 2 times 1 over 4, half. What was this? It was 1 over 8 sinc k pi over 2. That's it for all k. Right. So that we have already done that. Now, let's see if we can apply this linearity property and also the vertical shift property to get this. Y of t is a new signal that we are defining, and it is essentially 4x of t minus half, right? So what would that be? I need to, so on the right hand side here, the Fourier series coefficients of y of t, let us assume that they are b sub k. What would be b sub k? For 4x of t, what would I get? For 4x of t, will I get 4ak? Yeah? How about minus half? Go ahead. Except for k equals 0, right? So except for k equals 0, that would be that, right? So now what I can say is this. I can separate it out into two pieces. I can say this is going to be 4ak, the other guy is going to be 4ak minus half, right? This is going to play out when k equals 0, and this is going to be when k doesn't equal 0. Guys okay with that? And I can substitute ak in this if I wanted, right? So ak is not half, 1/8. 1/8 sinc k pi over 2. And also over here. So if you are asked to express it as a sinc, then you would express bk as half sinc k pi over 2 when k is not equal to 0, and it equals minus half when k equals, let us rewrite this here, bk half sinc k pi over 2 minus half when k equals 0, and it is half sinc k pi over 2 when k not equal to 0. Now, can you simplify the first one a little bit? When k equals 0, can you guys think of it, simplifying it a little bit? What is that? Just 0, right? All of this is just 0. Sinc 0 is 1. So sinc 0 is 1. Half sinc 0 minus half is half minus half, which is 0. Also, think of this guy. What is the average value of this guy? Half of it is below 0, half of it is above 0, so average should be 0, right? So that's your b sub k, the Fourier series coefficients of this standard square wave that has been shifted, also scaled, but also shifted, right? The only thing that we did is move it down by half, is this. Questions about this example? The application of linearity and the vertical shift property. Going once. No? We can put this, next. Time shifting property. If we can do vertical shifts, then we can also do horizontal shifts. So this property is shifting a signal that is periodic in time domain, right? Delaying it or advancing it, moving it left or moving it right. What does it do to the Fourier series coefficients? That's the question. Now, I hope that you guys are quick to conclude that you are not going to be changing a sub 0, the DC term, because if I move things left or right, I'm not changing the average of the signal. The only thing that I'm changing is all the other Fourier series coefficients, but I'm not changing the average. So a sub 0 remains as is. Let's take a look at the property. Let's go through the proof, and you will be, so in my opinion, this time shifting property is one of the very frequently used properties. You use it in a lot of situations. You're starting out with x of t. That's your periodic signal. Fourier series coefficients of that, a sub k. Then we are shifting x of t. In one case, we are delaying it by t0. In the other case, we are advancing it by t0, minus, then plus, respectively. The Fourier series coefficients of that, we are calling that b sub k. The property says that the Fourier series coefficients of the shifted waveform is ak, the Fourier series coefficients of the original signal, multiplied by e to the plus or minus j k omega naught t naught. How do you know omega naught? How do you know t naught? Omega naught is what? 2 pi divided by t. Cap t being the time period of the signal that you guys are working with. T0, what is that? Well, that's the amount of shift you did, delayed it or advanced it. So you guys both know both of these depending on the signal and given the amount of shift. You just need to plug it in there. Give it, if AK is already given, maybe it's the standard form. You already know that. You can just apply it over here to find BK. So let's try to see what each individual thing is. AK, what is that? Old coefficients, right? Fourier series coefficients of the signal before the shift. K is the coefficient index or the kth harmonic, right? That's the index to denote DC term, first harmonic, second harmonic, and so on. Omega naught, which is simply 2 pi divided by t. T is the time period, 1 over t is the fundamental frequency, omega naught is the fundamental radian frequency. T0 is the time shift, 2 seconds, 10 seconds. BK are your new Fourier series coefficients. Fourier series coefficients of the signal that has been shifted. Start the way we usually start. AK equals 1 over t integration over one time period x of t e to the minus jk omega naught t dt. An integration formula to compute AK. What would be BK? BK would be Fourier series coefficients of x of t plus or minus t0. So instead of x of t, plug in x of t plus or minus t0. That's the only change. Everything else is as is. Now, x of t plus or minus t0, let's try to just sort of do it for one case, x of t minus t0. Because the other case, once we do this, you will see that it is going to be the same, just including of the other case, sign case. So let's try to limit this to only the minus so that we can continue with this proof. Change of variable, t minus t0 is v, right? Some variable v. If v is t minus t0, you will have a change in lower limit, you will have a change in upper limit. What would be the change in lower limit and upper limit? You see 0 minus t0. So minus t0 will be the lower limit. Upper limit, t minus t0. So cap t minus t0 will be the upper limit. Yeah, you change the limits. Also, dv equals dt. Now you are able to write b sub k after the change of variable has been performed. You will have 1 over t, you will have minus t0 here, cap t minus t0 there, x of v e to the minus jk omega naught t dt. So you will be able to write that. Oh, by the way, t we have represented it this way. Now you can break up this exponential into two pieces. You can have e to the minus j k omega naught v multiplied by e to the minus j k omega naught t naught. One of them is going to be independent of v. This guy is going to be independent of v. Let me show you what is independent of v. E to the minus j k omega naught t naught is independent of v. So you can pull it out of the integral. You are left with 1 over t as is. You brought out that exponential with t0 out. The integration is from minus t0 to t minus t0, x of v, e to the minus j k omega naught v dv. What is this? Minus t0 to t minus t0. It is still integration over one time period. It is a different time period, but it is still one time period. 1 over t, integration over one time period. X of v, e to the minus j k omega naught v dv. What is that? Fourier series coefficients of x of t, right? So that will simply boil down to ak e to the minus j k omega naught t0. So that happened when it was a delay. Considering t0 is positive, it was a delay. Then you get to a minus. If you conducted the same proof with a plus, you would get a plus over there. So that proves the time shifting property or the horizontal shifting property. Questions about the property and how we proved it? Let us apply it. Oh, before we apply, let us try to make things a little bit more confusing. Was that? Just what you need, yes. Here, I don't know why, but if I preface that conversation with, let's try to make it confusing, I've already set up the premise, right? It is going to be a little bit confusing. I don't know, it has worked for me. Let's see if it does this time. Let's try to take a look at the Fourier series coefficients of the signal before and after you shifted it. What was it? Bk equals ak multiplied by e to the plus or minus jk omega naught t naught. That's what we proved. That's your time shifting property. Now I want you guys to start observing the magnitude change and the phase change. Let's try to look at the magnitude first. Ak, a complex number. Bk, a complex number. Let's try to find out the relationship between Bk and Ak in terms of their magnitudes first and in terms of their phase next. So how about the magnitude? If you take the absolute value of Bk on the left side, you have absolute value of the right hand side as well, right? The magnitude of Bk here, magnitude of Ak multiplied by e to the plus or minus jk omega naught t naught. Next, the magnitude of two complex numbers that are multiplied is what? Magnitude of Ak multiplied by magnitude of e to the plus or minus jx. Now we don't need any proof for this, but I hope you guys all agree. Magnitude of e to the jx is going to be a 1, right? Because square root of cosine squared plus sine squared, a 1. So if this guy goes to a 1, then you are left with what? The magnitude of Bk is the same as magnitude of Ak. So there is no change in the Fourier series coefficients in terms of their magnitude, right? You guys see that? Magnitude is the same. Time shift operation doesn't change magnitude of the Fourier series coefficients. That's one conclusion. Next question is, how about the phase? Well, Bk, let me go here. Bk complex, Ak complex multiplied by that, right? So whatever the phase of Ak is, you are adding or subtracting k omega naught t naught to it, right? You're adjusting the phase by k omega naught t naught. You're doing it either as a positive number or as a negative, plus or minus, depending on delay or shift, delay or advance. So in terms of phase, the phase of Bk is phase of Ak plus or minus k omega naught t naught. Phase is getting changed. magnitude of the Fourier series coefficients is not going to change. Now let me zoom out and say the thing that you will hear most likely, which is sort of related. We have looked at the details. What you hear is this. Time delay corresponds to a phase shift. That's what they mean. It doesn't do anything to the magnitude of the Fourier series coefficients. It just changes the phase. Questions here? Good. So you are going to have to look at it in terms of two sketches, with respect to K, magnitude, with respect to K, phase. Magnitudes are the same, but the angles are getting added or subtracted depending on that value, right? So when you are trying to say plot phase, say in radians, then you're doing 0, pi over 3, pi over 6, pi over 6, pi over 3, right? And you're adjusting that for each K value by K omega naught T naught. So does that make sense? So with respect to K, you're doing a magnitude. All right, here, let me sketch. But it's a good idea. Sketch it. If you sketch it, you get more understanding of it, right? So here you have two sketches. One is magnitude of BK, and the other is phase of BK with respect to K, right? And you are evaluating it as 1, 2, 3 here, 0 here, -1, -2, negative for both, right? K is an integer. Over here is going to be the same as AK, whatever it was. Over here is going to go up or down, right, for each K value by K omega naught T naught. Whatever the phase was for AK, say pi over 6, and you are changing by pi over 6, it will go plus pi over 6, pi over 3. You guys see that? So that will, the top one will remain as the same. Magnitude is going to remain the same. Next. Talked about this. Let us apply it. Over here, we are applying linearity as well as time shift property. So our goal is what? Our goal is, I've given you some periodic square wave. Find the Fourier series coefficients of this guy. There are some problems. One, it is not centered at 0, which was the case with our standard result. And there is a small problem. The small problem is the amplitude is 2 instead of being 1. So let me write out. So that's our goal, right? So this is a periodic signal. Amplitude is 2, and it is on from 0 to 2 and so on. Let us try to find out the time period omega naught first, because that's what we do. What is the time period for this? Four, and omega naught will be pi over 2, right? What do we know from a standard result? We know this. If there is a pulse train, right? This was our pulse train. T1, T. Pulse train 1,4. For that, we had 2 T1 divided by T sync K omega T1, K omega naught T1. If you plug in all the numbers from this, you will get this guy. Half sync K pi over 2 for all K. We have kind of seen this a few times now already. Cap T is 4, omega naught is pi over 2, T1 is 1. So you know it's pulse train 1. So we know this, we want this, right? So how do you go from this guy to this guy? Your goal is going to be express, you want x of t, right? So express x of t in terms of y of t. Change in amplitude 1 to 2, right? 1 to 2, so you need a 2 there. Also, you have to shift y delayed by 1 second to get to this, right? If you move this guy right by 1 second, you get this. You have to delay it by 1 second. So that would be y of t minus 1. So if you try to express x of t in terms of y of t, you have got twice the amplitude and a delay by 1 second on y. So what would be the Fourier series coefficients of x? We are calling that ak. What would be ak? Someone wants to attempt? Go ahead, Franklin. Oh, you are going for it directly. Okay. I was going to say, like, you want to do 2 times half. You are going straight for it. Okay. All right. Hold up. Let me write the 2 times half here. All right. Yeah. Sink. So k pi over 2 takes care of the sink. Done. What else? Yeah. Negative or positive? So negative here, negative there, right? Okay. Next. Uh-huh. Times. Good. You're done. Now let's try to find out why we got what we got. This was 2, so we scaled it by 2. For y of t, we had ak, bk. For y of t, we had bk. So all of this is our bk. And then there was a time shift of 1 second that allowed us, that made, we had to make sure that we multiply by the phase term there, e to the minus j k omega naught t naught. Omega naught pi over 2, t naught 1. Can we simplify this? Someone? Right, sink. Okay, sink. We can't do anything about the sink, right? So sink remains as is. We have k pi over 2. Okay. So how about e to the minus j k pi over 2? What is that? What is e to the j pi over 2? Just j. So e to the minus j, oh, what would be minus? Negative j. All right. So what would be e to the minus j k pi over 2? Yeah. Now, the only thing that I have to worry about over here is what? At the very end, after you solve your Fourier series coefficients, you have to worry about one thing. What is that? The DC value. Is the DC value included in this general form or not? So what would be our area here? So A sub 0 should be 4, right? No. Area divided by time period. So 4 is area divided by time period is what? 4. So it's 1, right? So A sub 0 should have been 1. Is it included in this? If you plug in a 0 over here and here, you get a 1. Absolutely you do. So you can say, now you can say this applies for all k. Because now you checked that the 0 term also is included in that. If it wasn't, then you would have to write it as a bracket notation. Questions about this? Let me just box this up. That's our answer. Good.
What's the sign of a decree?
Yeah, T0, either you are delaying or advancing. So if you're delaying, you get -1, -2, -3, right? T minus 1, T minus 2, T minus. Then you get e to the minus jk omega naught. So it's the same as this here, you see? if this is plus or minus, this is plus or minus. Yes. Whatever floats your boat, it is. uh, to distinguish that it is capturing both cases. Okay. So next we have time flipping property. What happens to the Fourier series coefficients if you take the signal, flip it about the y-axis? If x of t has the Fourier series coefficients of a sub k, then the Fourier series coefficients of a time flip version of x of t, defined as b sub k, is simply a sub minus k. What are we doing here? We are taking the Fourier series coefficients of ak and we are flipping it about the vertical axis. So a1 becomes b minus 1, a2 becomes b minus 2, b minus 2 becomes a1. You're just flipping it, right? Proof. AK integration formula. BK includes x of minus t instead of x of t. I need to get rid of this minus t. What will I do? I'll do a change of variable. V equals minus t. If I have got v equals minus t, my lower limit multiplies by negative sign, it remains at 0. Upper limit multiplies by negative sign, becomes negative cap t. dv becomes negative dt. Put all of those guys in bk, what do you get? Negative 1 over t. This negative is because of this guy, right? dv is negative dt. Upper limit changed from t to negative t because of this minus. 0, 0, that remained as is because you're just multiplying it by a minus sign. This became x of v, e to the j k omega naught v dv. Do some manipulation here. If you use up the negative sign there, you can flip the integration limits. 1 over t integration from minus t to 0, x of v e to the plus j k omega naught v dv. Since x of t is t periodic, if you take the integration from 0 to cap t or from negative t to 0, should be the same. So this integration you can replace with this integration. It's over one time period. So 1 over t remains as is, x of v remains as is, e to the plus j k omega naught v remains as is. So the only thing that changed is what? If you look at this formula, and if you look at this, the only thing that changed is this minus sign, which means there is a flip in k. So you can write it as a sub minus k. You guys see that? Let's try to sketch something here. K here, some AK there, and this is BK here, which is A minus K, right? Suppose I'm given, you are given A sub K. Let us say for 1 and 2 and 0 and negative 1 and negative 2, right? You have some value there, some value there. I'm just going to be writing them as some complex numbers. Don't worry about, I'm capturing both the magnitude and phase in one. I'm just writing it as a complex entity. So I'll say this guy, no DC term. I'll say this is say 1 plus 2j minus 1 minus 2j. Don't worry about the axis here. That doesn't make sense at all. Negative 5, negative 2j, negative 10, negative 10, 2j. All right. Right. Some complex numbers. When you try to sketch that for BK, all you're doing is what? flipping it about the y-axis, right? So this one will be 1 plus 2j, negative 1, negative 2j, negative 5, negative 2j, negative 10, negative 2j. Flipped about the k-axis. Questions here, what does a time flip do to the Fourier series coefficients? B1 is a minus 1, B2 is a minus 2, B3 is a minus 3, and so on. Similarly, on the other side, the Fourier series coefficients also get flipped. Time derivative property, one of my favorites. It'll become your favorite as well. The moment you talk about parabolas and cubic functions, if you're not using a time derivative property, then you are looking for a lot of trouble doing that integration. So if you delay the signal in time domain, you're doing something in the Fourier series coefficients. If you move the signal up and down vertically, you're doing something in the Fourier series coefficients. So if you're differentiating in time domain, are you changing the Fourier series coefficients? The obvious answer is yes. We'll just try to figure out how are you changing it. So let's say we start off with x of t is ak. X of t is our time domain signal. Ak are the Fourier series coefficients of x of t. Then if you differentiate the signal in time domain, then you essentially multiply ak by jk omega naught. If you differentiate the signal in time domain, then you multiply the Fourier series coefficients by jk omega naught. That's it. So a quick question for you guys. Suppose you want to try to find out the Fourier series coefficients of a triangular waveform. What do? You can use the derivative property. Because once you derivate a triangle wave, what do you get? Square. We know the square wave standard form, right? We have moved it here and here, we have moved it out here and here, we have done all the combinations with the square wave. So if you wanted to try to find out the Fourier series coefficients of a triangle, let me show you here. Triangle. I want to find out AK, right? The Fourier series coefficients of triangle, I want to find out. What do you do for this? You differentiate. If you differentiate that signal, what do you get? You get square. Yeah? You know the Fourier series coefficients of square, right? You know that, BK. What you really wanted was AK. So how do you go back? Oh, by the way, what is BK? Can I say BK is JK omega naught AK? When you differentiate it in time domain, you literally multiplied by JK omega naught in the Fourier series, right? So how do you find out AK? Because that's what is that? Just divide it. We are able to divide it because k is an integer. It is discrete when it comes to the frequency. You know when we will not be able to divide it? Oh, no. So k equals 0 is a separate conversation. So literally what we do is this. We do this, we find AK, we find a sub 0 of this triangle, area under divided by the time period. Then we will see if it is included in this or not. If it is, then we will write it as for all k. If not, we will write it as bracket notation. K equals 0, k naught equals 0. So we'll do it with respect to the triangle. But what I'm trying to say is, here is a sort of, think about your procedure. You have differentiated the time domain signal. So you should have some integration to go back. You didn't integrate, right? Because the reason why you didn't integrate was because Fourier series, those are discrete values. So a division took care of all the values for each k. But when you talk about Fourier transform, the same property will come in, a time derivative property for a Fourier transform. In that case, you will have to do an integration back. So when you do the time derivative, and then at the end, you will have to integrate it back. So that's one sort of a very key difference between how you apply a property in Fourier series and Fourier transform. In Fourier transform, for this particular property, there will be an integrating it back step. Over here, it will not be there. But I hope you guys are okay with this conversation. Now, let's make it a little bit more interesting. Let's bring this down. How about that? Parabolas are quadratic, right? So you can still do this to get a triangle. Now, if you wanted to find this, say C sub k, what do you do now? You wait. That's it, right? So when you differentiate it once, you go to a triangle. You differentiate it twice, you go to a square. But when you're writing it for a square, this is not just, so this is what? This is AK. J k omega naught ck, right? And when you differentiated it twice, this became j k omega naught squared ck, right? You guys see that? Now, when you want to go back, you divide it once, you divide it twice. So this would be what? C b squared. You guys okay with that? Yeah? All right, let's do one more. Things going up should be straightforward now, right? Parabola, cubic, fourth order term, fifth order term, like keep going up. The power over here will keep increasing, right? How about down? What happens here? So when you differentiate a square, what do you get? Impulse train, right? Impulse train, do you know the Fourier series coefficients of that? Yes, Fourier series coefficients of impulse train 1 over t everywhere, right? So you could go here and you could also evaluate the result of the Fourier series coefficients of impulse train is also a standard result. So you can use a standard result for square, or you could use a standard result for impulse train, up to you. There's a difference. If you use it for square wave, you will have it as a sink, right? You will have a sink in there, which means that there is already some math that has already been done for you. For example, taking the e to the minus jx plus e to the plus jx minus e to the minus jx divided by 2j is a sign. That part of the math has already been taken care of for you. If you use the impulse train, then you will have to do all that math, right? So the simplification will take a little longer. All right, questions about this discussion? I hope you see the usefulness of this time derivative property. You could go up as high as you want in terms of the power, right? Any function, polynomial function, periodic, which is periodic. Now you know the Fourier series coefficients of that. All right, let's come back to this. Let's prove it. Differentiating it, does it really do that? So let's say we have AK, Fourier series coefficients of x of t. 1 over t, integration over one time period, x of t is a minus jk omega naught t dt. We have seen this like 315 times. Bk, what is that? Bk is the Fourier series coefficients of the differentiated signal, right? So 1 over t, 0 to t, differentiate x of t with respect to time once, e to the minus jk omega naught t dt remains as is. Next, use the integration property. You have got this u here, which is e to the minus jk omega naught t, dx is dt, dv by dx is dx by dt, which equals u times v minus integration v du divided by dx multiplied by dx. If you use all that property, you get this. It'll expand to this. 1 over t, the result of that integration is x of t e to the minus jk omega naught t, integrating from t to 0 to t, plus jk omega naught, integration 0 to t, x of t e to the minus jk omega naught t dt. I have simply applied this to get that. Note that when you plug in a cap t over here, followed by this 0 over there, it is a periodic signal, right? If it's a periodic signal, the value at 0 and the value at one time period after will be the same. That's how it's defined. So upper limit and lower limit are essentially evaluating the signal at the same value, which means all of this will go to a 0. Oh, sorry, right here. What you will be left with is just simply jk omega naught followed by ak. Right? All of this is ak. Questions about time derivative property, how it could be useful, how we have proved it. The proof of all these things are essentially, start off with an equation for ak, then plug in the new signal, apply change of variable or some property of integration, simplify. Okay. We need to find this. We are doing the simple triangle to square now. What do we have here? We have a triangle looking waveform. It has an amplitude of 1 here. Let's try to find out what? The thing that we try to find out first for everything. Time period, omega naught. What is the time period? 4. What is omega naught? Pi over 2. Next. I could also find a sub 0 at this time, or I could do it later. Let's just try to finish it off. What is a sub 0? A sub 0, the Fourier series coefficients of this guy, we are calling that ak. We don't know them, so we need to find them out. But we are trying to find out a sub 0 here first. What would that be? Area over one time period divided by the time period, right? So what would be the area over one time period? Half base height divided by one time period is what? 4, right? Half. Is that okay? So a sub 0, we have evaluated it. Let's keep it on the back burner for now. Let's move on. The triangle waveform, the Fourier series coefficients of the triangle waveform are not in the standard form. So I'm going to differentiate it. If I differentiate the signal x of t, I get y of t. What does y of t look like? Positive slope, negative slope, positive slope, negative slope. So I get a square wave. But this square wave actually is centered at 0, right? That's not our standard form. Our standard form is somewhere else. Let's see. What is our standard form? Our standard form is this. Somewhere like that, right? So this is 1. This is t1. This is negative t1. This is 0. This is t, right? That's our standard form. And if this is this, let's call this pulse train. t1 comma t, the Fourier series coefficients of that are 2t1 divided by t sinc k omega naught t1 for all k, right? That's our standard form. So we're going to have to use that later on. Let's try to find out what bk is. Now, can I express x of t? X of t is that, it's taken. Y of t is this. I need to find bk, right? What do I know? I know standard form here. So let's call this c of t, right? Can I maybe pick the values of t1 and t to match this guy here? What should I use? What would you pick for t1 and t? I think t is very obvious. T1 is the problem. You need Fourier series coefficients of this. You have this. What would you pick for t1? Like what value would you want here? Go ahead. It has to be symmetric about the y-axis, right? Shifted by how much? 1, right? So if you pick 1, this is -2, this is 0. If you pick -1 to 1, it would have been there, right? So you use it, then you move it back. Do you see that? So let's try to pick t1 as 1. Got 1 here, -1 here, and so on. How about t? That should just be 4, right? Time period is still 4. So this is just 4. If you substituted t1 as 1, t as 4, what do you get? Half sinc k pi over 2. Yeah? So you've got this, right? So you've got c of t as this signal. Now I want you guys to think about how can you express y of t in terms of c of t. So you have to say y of t equals blank. Use c of t there. What do you need to do? Do you need to do something to the amplitude? Here. The amplitude of here, this guy is 0 to a 1, right? So if you want to write it for y of t, you need to bring it down by half. Bring it down by half, yeah? All right, so I can say minus half later. What else do I need to do? Peak to peak is 1, over there peak to peak was 1, so I don't need to do any change for the amplitude, right? Okay, how about C of? I need to do some delay or advance. What do I need to do to C to get to Y? T plus 1, there it is. If I advance this signal, I get this, right? I'm trying to write Y in terms of C. So that would be a plus 1. C of t plus 1 minus half. You guys agree with that? Yeah? Now let's write bk. What would be bk? Let me erase all of this now. C of t plus 1 minus half. What would be bk? Because of that minus half, let me write it in two things. Bracket notation. K equals 0, k doesn't equal 0. When k equals 0, what is it? C of t plus 1, right? C of t plus 1 will give you what? Half sinc k pi over 2, that is for C of t. You multiply it with what? E to the plus j omega naught t naught is 1. Yeah? and then minus half for this, right? When k is 0. Yeah. Next, when k is not equal to 0, what is it? Simply half sinc k pi over 2 multiplied by e to the j pi over 2. Done. Yeah. Good. I can do that. Sure. Yes, I can do that. When I have k equals 0, what happens? All of this goes to a half, right? All of this goes to a half, right? And minus 0. So 0, it becomes 0, right? Oh yeah, that's exactly what we have here. It's half of the time it's up and down. So it should be 0, and we are on track. What about this? Hold on, we are missing a k. E to the j k omega naught t naught. There's a k there. Can we simplify this guy? J to the k, right? All right, so we got bk. What is that? J to the k half sinc k pi over 2, yeah? Can we write bk in terms of ak? Let us write it over here. bk, can I say that it simply equals jk omega naught ak? We differentiated in time domain, so our Fourier series coefficients get multiplied by jk omega naught. That's the differentiation property, right? We have found what? bk. What was bk? Half sinc, oh, not half, it was j raised to k half sinc k pi over 2 equals j k omega naught ak, right? This is k not equal to 0 here. Yeah, we wanted ak. What do you get? J k minus 1, right? Is that okay? What is omega naught? Let me write omega naught here. Pi over 2, which means this 2 can get cancelled. And then you can just have a k and a pi here. Sinc k pi over 2. Is that okay? This is for k not equal to 0. I think we are ready to write our final answer. Ak equals half when k equals 0. Yeah. And when k doesn't equal 0, we have got j raised to k minus 1 divided by k pi sinc k pi over 2. I think I copied it, right? Yes. Questions? So you use the time derivative property, but you also have to use that standard result in a little, what you have is the standard result. You may need to move it up or down, left or right. In this case, you had to use the time shift property as well. Questions? Good. No, it doesn't. That's why I was not doing it. I was not doing it. That's the reason. But it is helpful. In this case, it was helpful because it allowed me to check whether I'm on the right track or not. The moment I got 0, I said, oh yeah, it is supposed to be a 0, right? For this guy, it is supposed to be 0. But yeah, you're right. It doesn't play a role. And that's why I evaluated a sub 0 first. Wanted to do it so that I don't forget it at the end. Let's see. Other questions about this example? A few years ago, I gave a problem very similar to this on the exam. It had parabolas instead of triangle. They were parabolas instead of a triangle. You know what happens when you have to deal with that? When you have parabolas, when you differentiate it, you might get very nice square waves, which can be combined using just one pulse. Sometimes you may get two different pulses, right? So some guy going up and some others that are shifted going down. If that is the case, then you need to treat it a little bit differently. You need to treat it as two different periodic signals, right? Fourier series equations. This, add them up, then later on divide by jk omega naught to get back. But the better you get at using these properties, the simpler this process becomes. Questions here? Can we talk about some of the places where mistakes can easily be committed here? In my opinion, a lot of people make mistakes here. The way you express y of t with the rectangular pulse train, a lot of them just make it a minus there, right? So you need to know what you have and what you are trying to achieve, right? Okay, let's see. Right, so we have actually done this problem, which is to obtain BK using vertical and horizontal properties. We fixed that. We do that for all things that are non-zero. And then at the end, we divide it by jk omega naught to include, to find AK. Also evaluate the a sub 0 value, which we did first, actually. That remains as is. Right? So our answer is right here for this problem. No other questions about this? Going once, twice, sold. All right, let's start backwards. I'm starting the next lecture with the last slide because I think this is a good thing to talk about. So I have I think we included, yeah. I think we are okay. All right, so the goal of this is to find the Fourier series coefficients of a cosine. How many frequencies does a cosine have? One, right? So whatever you have, you will have it at b sub 1 and b sub minus 1. First harmonic, that's it, right? You will have only one. How about a sine? Again, only one tone, single tone, right? So you will have something at a sub 1 and a sub minus 1. My goal here is to find the Fourier series coefficients of a cosine that has an amplitude of A and a frequency of, well, a radiant frequency of omega naught and a phase of theta. Using Euler's, I can write x of t as A remains as is. For the cosine, I'm going to write it as e to the jx plus e to the minus jx divided by 2. So I've got e to the j omega naught t plus theta plus e to the minus j omega naught t plus theta divided by 2. So far, you guys agree with that? Yeah? Using Euler's, right? That's just using Euler's. Yes, all right. Now, let's try to break it up. A divided by 2 e to the j omega naught t multiplied by e to the j theta for the first term plus a divided by 2 e to the minus j omega naught t multiplied by e to the minus j theta. So I've just broken up into multiple terms here. I'm still writing this as another form of a cosine omega naught t plus theta. Fourier series coefficients are what? A sum of overall k, a sub k e to the j omega naught t, right? Sum of all the projections. So this and this have to be the same, right? For the same x of t, for the same cosine, this is a cosine. This, if I assume that this is also representing a cosine, I can start comparing coefficients. What coefficients will matter and what will not matter? You see, here you will have k going from negative infinity to infinity. However, over here you will have k as 1 and k as negative 1. That's it. Those are the only two, right? You see that? All the other terms, the coefficients are 0. All the other Fourier series coefficients are 0. So if you compare the coefficients, what do you get? A sub 1 is a divided by 2 e to the j theta. A sub minus 1 is a to the divided by 2 e to the minus j theta. That's it. So the Fourier series coefficients of a cosine are what? A sub 1, a sub minus 1, a divided by 2. How can you express this in a different form? Well, you can talk about the magnitude and phase, right? What would be the magnitude? What is the magnitude of a word? A over 2, right? A over 2 here and a over 2 here, right? So on a scale, on a k axis, you will get a over 2 there, a over 2 there. That's it, right? Nothing else. Too big. You will get something here and something here. That's it. This is k. This is what? Magnitude of a sub k. This is at 1, this is at negative 1, this is 0. The value, a over 2. The value, a over 2. I see that? What about the phase? What is the phase going to be? So, theta and negative theta, right? Theta for this guy, negative theta for this guy. Yeah? At 1, theta. Negative 1, negative theta. Is that okay? Is cosine an even signal, odd signal? What are we doing? Even. For a signal that was real and even, the magnitude of the Fourier series coefficients even. The phase of the coefficients odd. You start seeing symmetry in those, right? So there will be symmetry properties for the Fourier series coefficients. Over here, for the magnitude, it's even. For the phase, it is odd. You guys see that? Yeah? Can you also express this in using delta functions maybe? We'll do it later. Let's see. Let me go back here. Let's start lecture 10. Few minutes left. We are going to continue our properties. So this lecture is going to be sort of our, after this, whatever we have left is properties of Fourier series. Then we'll get into Fourier transform. So symmetry properties of Fourier series will be what is left after this. We are going to continue our properties. So far, linearity, time scaling, sorry, not time scaling, shifting it horizontally, shifting it vertically, differentiating it. Now we are adding time scaling property, conjugate, Parseval's theorem, multiplication. So let's talk about multiplication. If you are multiplying two signals in the time domain, what do you think happens to the Fourier series coefficients? Multiplication, convolution, right? Multiplication and convolution. If multiplication is happening in one domain, convolution is happening in the other domain. Time frequency. Fourier series is a frequency domain information, but discrete. So if you're multiplying two signals in the time domain, you're evaluating their Fourier series, you're convolving the Fourier series coefficients. And the other way, right? So if you're convolving the through in time, if you're convolving, then you're multiplying in the frequency or even the coefficients. So let's start with time scaling and then move into it. So time scaling property, if you have x of t, it's a periodic signal with some time period cap t, and if the time period is t, omega naught is 2 pi divided by t, what would happen to the scaled, time scaled version of x of t? Well, first, x of t can be represented as this summation. This is the summation of all the projections of the orthogonal set comprising of complex exponentials. Ak e to the j k omega naught t. K is going from negative infinity to infinity. Now, let us say that alpha is greater than 0. We are just doing a time scaling. No flipping is involved here. X of alpha t. So we have squeezed the signal or we have expanded the signal, right? Depending on whether alpha is greater than 1 or less than 1. X of alpha t is also going to be periodic, but the time period is going to be t divided by alpha. Now, if time period gets a scale of divide by alpha, then the fundamental frequency also gets that same scale. Omega naught prime will be alpha omega naught. Now, if you have a signal that has a time period of t divided by alpha and omega naught of alpha omega naught, how are you going to express it as the sum of all those exponentials? X of alpha t equals summation of k equals negative infinity to infinity. What do you have here? Ak e to the j k alpha omega naught. The thing that changed is this because of this. T. The Fourier series coefficients, when you scale the signal, the Fourier series coefficients do not change. What changes is the Fourier series itself. You guys see that? The Fourier series is changing because instead of evaluating it at e to the j k omega naught t, you are evaluating it at scaled versions. So the orthogonal set itself is different, but the coefficients are not different. They are the same. So this, you can ask two questions. When a signal gets time scaled, squeezed or expanded, do the Fourier series coefficients change? That's first question. And the second question is, does the Fourier series change? No here, yes here. The Fourier series itself has changed. The set of orthogonal functions is no longer e to the j k omega naught t plus or minus e to the j k omega naught t. It is now e to the plus or minus j k alpha omega naught t. The orthogonal set is different, but the coefficients that are associated with that for each k are the same. So the Fourier series coefficients don't change. The Fourier series changes. Let's see. Conjugate property. What happens to the Fourier series coefficients if you evaluate the conjugate, complex conjugate in the time domain? Given x of t is a t periodic signal. T periodic signal means what? It's periodic with time period t, right? And we are given that the Fourier series coefficients of x of t are defined as a sub k. Then y of t, which is simply the complex conjugate of x of t, its Fourier series coefficients are defined as b sub k. The relationship between b sub k and a sub k is going to be bk is a sub minus k complex conjugate. So think about this. What is happening here? You are flipping about the y-axis, and you're also flipping about the x-axis, right? Because complex, here, let me try to go back to this guy. Right. Over here, earlier when we did the flipping about the k, right? This was ak, this was a sub minus k. We move these two guys, we flip this over here, we flip this over here, right? But now, along with that, each of these guys is also getting conjugated. So this one will become 1, negative 1 plus 2j, 1 minus 2j, negative 5 plus 2j, negative 10 plus 2j. They are getting flipped here to here and also getting complex conjugated. Guys see that? Yeah? So that's the effect of finding a conjugate in the time domain. So that's what that means. Let's prove it. AK, integration over one time period, 0 to t, x of t is a minus jk omega naught t dt. Fourier series coefficients of a time periodic signal x of t. B sub k, what is that? Fourier series coefficients of x complex conjugate of t. Everything remains as is, except now you have x of x complex conjugate instead of x. Now, what we can do is we can move this complex conjugate operator outside by reversing the sign of this complex exponential. We are making this guy a plus. We have removed that complex conjugate out over here. Everything else remains as is. 1 over t, integration 0 to t, everything is as is. Now, if you see this, what is that? These are Fourier series coefficients of a sub minus k, right? The only thing changes is here. So all of this is a sub minus k, and then the complex conjugate carries over here. So you do a flip about the vertical axis, and also each Fourier series coefficients gets complex conjugated. Now, let's try to see what happens when x of t is real. If x of t is real, then we can say that x complex conjugate is the same as x of t. We can say that. If that is the case, then the Fourier series coefficients should also be the same. If a sub k, in that case, will equal a sub minus k complex conjugate. That is for the Fourier series coefficients. Think about that. The complex coefficients, complex conjugate coefficients on the right half are the same as the left half, right? All of these should be the same as these. Can you see that? This should be the same as this. But also, this should be the same as this after even conjugating them, the complex conjugating them, right? Because of that. So that's with respect to the Fourier series. Now let's try to observe magnitude and the phase. The magnitude of AK is the same as the magnitude of A sub minus K complex conjugate because of this. Magnitude of a complex number, conjugate number is the same as this, right? You go A plus J, A plus JB or A minus JB, you're going the same thing, square root of A squared plus B squared, right? So you're going the same distance. So it's the same thing, A sub minus K magnitude. AK magnitude is the same as A sub K magnitude, which means that the magnitude is even. When the signal is real, the magnitude of the Fourier series coefficients have even symmetry. Where have we seen this before? Last slide. Cosine signal was even real. Our magnitude of the Fourier series coefficients had even symmetry, but our phase had odd symmetry. If I go back over here, you will see that the phase will have odd symmetry. Where is that? Right here. Phase of AK is going to be the same. This is this, right? So phase here should be the same as phase here. What is the phase of A sub minus K complex conjugate? A plus JB, when you conjugate it, the phase becomes A minus JB. Phase gets reversed. So you have minus phase of A sub minus k. Phase has odd symmetry, magnitude has even symmetry for all real signals. Questions about this? Find the Fourier series coefficients of the real part of x of t. Now, in order to do this problem, we are going to use this simple property here, which is if you have a complex number z defined as x plus yj, jy, the complex conjugate of complex number z is what? X minus jy. And if you add these two up, z plus z conjugate, what do you get? 2x. Also, 2 times the real part of z, because the real part of z is x. So if you want real part of z, what you have to do is z plus z conjugate divided by 2. Let's see that. Okay. So with that, let's get into it. What is the find the Fourier series coefficients of real part of x of t? Let's start with x of t. What is the Fourier series coefficients of x of t? Let's define them as ak. Right? How about x conjugate? X complex conjugate of t. What are the Fourier series coefficients there? A minus k complex conjugate. Yeah? That's the conjugate property, right? If you want real part of x of t, then what you need is x of t plus x complex conjugate of t divided by 2, right? That's the real part. Which means that this is going to have the Fourier series coefficients of what? Half a sub k plus half a sub minus k complex conjugate, right? Using linearity, I can write that. Yeah? You guys okay with that? Now, that's it. Those are the Fourier series coefficients of real part of x of t. And in the same manner, you guys can also find the Fourier series coefficients of imaginary part of x of t. What would that be? Imaginary part? This remains as is. This remains as it. Instead of real, this becomes imaginary. So if you want imaginary, what do you need to change? Minus if x of t is real, what happens to the Fourier series coefficients? This will equal this if x of t is real, right? And if x of t is real, then this equals this, which means the Fourier series coefficients of imaginary part of x of t will go to 0. Well, of course, x of t is real, so no imaginary component, right? All right, let's move on here to time multiplication property. I'm going to be stopping at a very, all right, we'll try. So what is time multiplication property? First, why did I talk about, I could have called it multiplication property. I felt the need to talk about it specifically, time multiplication property. The reason is you could be multiplying even in the frequency domain. So it's very helpful to sort of be explicit about it. You are multiplying two signals in the time domain. So time multiplication property. You have two signals here, x of t and y of t. Both of them are periodic with the same time period, cap t. Their Fourier series coefficients are ak for x of t, bk for y of t, and we are defining z of t as product of the two signals, x and y. So the property says that c of k, the Fourier series coefficients of the multiplied signal is simply the discrete convolution between A sub k and B sub k. Do a discrete convolution in the Fourier series when you are trying to multiply signals in the time domain. So that's the property. Now I don't want to spend time proving it because we have about 3 minutes left. I will do a problem first. Let us start boring a little bit at the beginning of next lecture, and then we'll do something interesting. Let's try to end this class on a high note here. So let's try to find this. Find the Fourier series coefficients of z of t, where z of t is defined as a product of a rectangular signal and a cosine. The square wave signal is pulse train pi over 2 and 2 pi. So that's t1 and that's t. And then you have your cosine t, right? So let's try to identify where we are stopping here. So this is t, this is t, this is my pulse train. Let's not do pulse train. What we'll do is we'll try to define this guy as x of t, and we'll try to define this guy as y of t. And then we'll say x of t has Fourier series coefficients a sub k, and y of t has Fourier series coefficients b sub k, right? For x of t, pulse train pi over 2. So that will make this pi over 2. This will be negative pi over 2. This will be 0. So what is this? 2 pi? Yeah, that's your pulse train, right? The amplitude is 1 everywhere there. So that's your pulse train. How about this guy? Here you have y of t, which is cosine t, right? Cosine t. This is 0. That is 1. Can somebody help me find what would be the time period of this guy? Omega naught is what? Omega naught is 1, right? So what would be t? That means what? This is pi. This is pi over 2, right? So imagine multiplying this with this. You are essentially chopping off all these negative ones. Your periodic wave, after you multiply, will have something like this: cosine, 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 cosine. Right? That will be your periodic wave. That's the signal for which you are trying to find the Fourier series coefficients. You guys see that? All right. So let's go back. Are we in a place where we can directly find x of t Fourier series coefficients? AK, what is that? 2t1 divided by t sinc k omega naught t1, right? So what is t1? Pi over 2. This guy is pi sinc k. What is omega naught? Time period is 1. Omega naught is 1. Time period is 2 pi. 2 pi divided by 2 pi 1. All right. So k multiplied by pi over 2, right? Can we simplify this a little bit? Pi gets cancelled. Okay. So this is just sinc k pi over 2, right? This is for all k. Is that okay? How about this? What are the Fourier series coefficients of cosine t? I'm calling the Fourier series coefficients as b sub k, right? I'm going to try to bk, right? Yeah, bk. In this one, where did I make the mistake? Here? Oh, This is 2. Oh, so there's half here. Right. Thank you. Yeah. All right. BK. What is BK going to be? I will write the answer first and tell me if you guys agree with it or not. There are two coefficients. One, k equals 1. The other, k equals -1. The amplitude of both of them is half. What did I use? I essentially used the first thing that I derived for you guys, which was right here. Theta is 0 and A is 1, right? Theta is 0, A is 1. What do you get? This cancels out. You get half here, half here. So half when k is 1, half when k is -1. You can write that as two impulses. An impulse at 1, an impulse at -1. Half delta of k minus 1, half delta of k plus 1. You guys okay with that? 1 minute. 1 minute. Here, I can't stop here. I can't. All right. So let's try to write the Fourier series coefficients of z of t. What is that? Fs of z of t equals, I hate these brackets. I need to convolve a sink with an impulse and another impulse. Good. That's it, right? So I got half there, half there. So 1/4. 1/4 sink k plus 1 pi over 2 plus 1/4 sink k minus 1. That's it. Good. Oh, yes. Excellent. How does it look like? A sink, a sampled sink sitting here and a sample sink sitting here. Too much? All right. We'll stop here. We'll pick it up on Monday. Thanks for bearing with me for the extra time today. Let's see. We meet on Thursday. Then you guys are off for summer break. Then we meet on Thursday, right? You're looking at me like, why are we meeting on Thursday? And then after break, we will do some other things. All right, stop recording here.